Hi, everybody. I hope that everybody's feeling well, healthy, not getting too nuts with being bundled up inside. Let's take a look at the photoelectric effect. Now, one thing that I didn't really go into a lot of detail with is this battery, this variable voltage source. Why do we do that? And why is it set up backwards? Well, remember there were two things we were dealing with here. One was how many electrons, they call them photoelectrons, come off per second and go over to this other plate and get carried through and go back through. And we can always tell how many photoelectrons are coming through and getting to the other plate by our ammeter. It'll tell us what our current is. However, the other thing we talked about was the kinetic energy on the electron, or the maximum kinetic energy. How can we tell that? That's what this voltage is for. Notice it's set up in such a way that it's going to set up an electric field in this direction. There would be my electric field going through there. Now, electrons get a force in the opposite direction of the field, which means this voltage here is going to act against the motion of the electrons and act to stop those electrons from going over towards the plate. It might stop it, it might not, depending on the energy of electrons and the voltage. Now, this becomes what we call a stopping potential. Okay? That acts like a stopping potential. And I can tell by varying this voltage what the energy electrons are, because when I get that voltage equal to what the maximum kinetic energy of these electrons are, it's going to bring them to that plate and just bring it to a stop. Now, let me show you. This is going to take me a second to set this up. And I'm going to share with you the link for this. Now, this is a Java applet, so it may take you a few seconds to get this straightened out, but here we go. Yeah, I'm kind of leaning my laptop up like this, but I think we'll be all right. Now, here's my light. Don't you even think about doing that. All right, there's my light against the plate. Here are the electrons firing off. I'm going to change the voltage. I want this voltage to be down to 0. There we go. Now notice, it's not that easy to do that. Here's my current. Here's the light coming through there. Right now, I don't want to see that. Right now, I'm only showing the highest energy electrons. Keep in mind, when the photon goes into the atom, sometimes all that energy gets transferred. Sometimes only part of the energy gets transferred to the atom. That's why you're seeing a range of different velocities coming out of here. But we want to just look at the maximum energy ones. So I'll let them all clear out, and we're going to get just the maximum energy ones here. Now, I lower my intensity, and I will get less photoelectrons coming off per second. And you can tell the current's gone down. It'll just show one every so often going through there. If I increase the intensity, I increase the number of photons going onto that plate, and I'll get more photoelectrons, and I'll see more current. Now, let's take a look at what that reverse voltage does. If I take this voltage, and you can see I've got positive on this plate, negative on that plate, you can tell that the electrons are slowing down and the current is going down. Eventually, if I get to the point that the electrons just barely make it to the plate, that means that it took 1.8 volts to stop those photoelectrons. That means I've got a stopping potential of 1.8 volts, or the electrons were coming off with an energy of 1.8 electron volts. Lower the voltage, and all of a sudden, some of the electrons start to make it over to the side, and I get a current on there. Now, one thing we want to take a look at here, and I want to put that up. Notice that if I play around with my frequency, or they should give me wavelengths, you're starting to get that graph that you guys were asked to draw last night. We're going to talk about that in a second. But that would be electron energy versus frequency. But this is your stopping potential. So if I know what my stopping potential is, okay, how much energy it takes to stop those photoelectrons, like right now, they're barely even making it there. Get a little bit more energy on those by putting more into the violet. And eventually I'll get to a point where some of the electrons do make it. Okay? Because I'm increasing the energy on the photons going in by going towards violet and ultraviolet. More energy is going on. And I'm starting to get a current through there. I'm going to share the link with you on this. It does use Java. It is picky. I tried to get it to work on a PC, and I had problems with that. I had to load a player for JAR, basically a Java player to get this to work on the computer. But you can play around with it and you can see what happens. Of course, if I show all of them, some of them have enough energy to make it, some of the electrons. Some of them don't have enough energy because the photon doesn't always deposit all its energy into the atom. It's almost like playing pool, where it may hit it obliquely and fire off bounce off the atom with some energy left in that photon. So we don't deposit all the energy on that. And we're going to talk about that a little bit more later on when we get to the Compton effect and stuff like that. All right, so let's say for argument's sake, it takes 2 volts to stop the electrons from making it to the plate on the right. So I've got this guy set at 2 volts right here. Okay, positive this side, negative that side. The electrons come off, they slow down, and just never quite make it to that negative plate. So my ammeter is going to read a current of 0. Okay, let's say it takes 2 volts to stop the electrons from making it to the plate on the right. We can tell because the current's 0. Well, you know the work that's being done is the charge times the voltage. 1 elementary charge times 2 volts is 2 electron volts. So these electrons are coming over 2 electron volts, and there's 2 electron volts of work being done on that to bring it to a stop. Since the work done stopping the charge equals the kinetic energy of the electron, the kinetic energy is 2 electron volts. I'll post these pages too with everything else, just in case you miss things as you go through. All right, you might want to print them before you start watching this. I may write that down in there. So let's take a look at our graphs that you guys were asked to plot. You'll notice that the 2 graphs are going to be nice and parallel to each other. And I've got a whole bunch of other things written down here that we're going to talk about in a second. And I will take a picture and I'll post all of this. We've got kinetic energy and electron volts and frequency in times 10 to the 15th hertz. So all these numbers are times 10 to the 15th. And the first question, well, first thing was to plot both of these kinetic energy versus frequencies. Now, you were asked to find the slope of the line. I picked silver. I picked the point where it crossed the axis, which is 1.2 times 10 to the 15th hertz. And that's the frequency. Kinetic energy is 0 right there. It's nice to pick something on the axis when you're finding slope. And I picked this point that my line went right through, which was a data point. It was, frequency of 5 times 10 to the 15th hertz and a kinetic energy of 15.9 electron volts. And I found the slope. And that's right over here. The slope is your change in y over change in x. 15.9 electron volts minus 0. 5 times 10 to the negative 15th hertz minus 1.2 times 10 to the 15th hertz. And I got 4.2 times 10 to the negative 15th electron volts times hertz. Or, because hertz is 1 over seconds, or seconds 1 over hertz, I'll get electron volts times seconds. Okay, keep that in mind. Now, the next thing, well, we were asked to find the slope. I've got it right here. Now, I was asked to change the slope over to joules, from electron volts per second to joules per second. Right on the front page of the reference table, I'll put it up here, 1 electron volt is 1.6 times 10 to the negative 19 joules. Right down the front page of the reference table, which makes it easy to change things over. I've got 4.2 times 10 to the 15th electron volt seconds times 1.6 times 10 to the negative 19 joules per 1 electron volt gives me 6.7 times 10 to the negative 34th joule seconds. Hold it, 4.2 times 10, that's 10 to the negative 15th. And if I take a look at those are both Planck's constant. I'm off a little bit, 6.63. I've got 6.7 times 10 to the negative 34th. I have 4.2, 4.14. Those are both Planck's constant. Whenever you plot frequency versus kinetic energy for the emitted electrons, the slope of these lines are always Planck's constant. Always Planck's constant. Sorry. Okay. Now, what else were you asked to do? The next thing you were asked to do was you were asked to define what the threshold frequency is. Well, that I'm doing for you. Threshold frequency is the minimum frequency to cause electron emission. And it's F naught is the symbol for this. So I come over here and I take a look, and the place where I've got just begin to start to get some energy out of this is right there. The point where the line crosses the x-axis is the threshold frequency. Any frequency above that point is going to cause emission. Any frequency below that point isn't going to cause emission, because the photon energies with the higher frequency are high enough to rip that electron away. Below that threshold frequency, there just isn't enough energy to cause emission. So for silver, I got a threshold frequency of 1.2 times 10 to the 15th hertz, where it crosses that axis. And for platinum, it's a little bit harder to get that guy to emit. It's got a slightly higher threshold frequency of 1.4 times 10 to the 15th hertz. Okay. So, there they are. Now, work function. We talked a little bit about this already. Work function is the minimum photon energy required to cause electron emission. Now, there are two ways of finding that. One way is by extending your best fit line as a dotted line until it reaches the y-axis. So, let's take a look at this. There's my chart. Understand, as I'm going down, my frequencies are getting less and less and less. Right there, I got a frequency of 0, which means there's no light hitting this thing. If I took a look at my chart here and continue these lines down, what this says is, at this point, I'm missing 4.7 electron volts. It's negative. Electron volts of energy to cause emission. That is the work function. That's how much energy it would take to emit it. I got to add that much energy to this to cause emission. For platinum, it's a little bit more. It's about 5.6 electron volts of energy where it crosses that axis. Clearly, I didn't do a regression on these things, so these lines aren't absolutely perfect, but we're going to be reasonably close on those two. So that's one way to find the work function, is to extend this thing down where it crosses the y-axis. That's going to be how much energy is missing to cause emission, or how much energy you've got to add to that to cause emission. Just going to take a sip of tea here. Okay. All right. Now, what's another method for finding the work function? Well, another method is using Planck's relationship. We know that our energy of a photon, I'll put a little pH there for photon, is equal to Planck's constant times the frequency. Well, considering that the work function is the minimum energy necessary on a photon to cause photoelectron emission, and the threshold frequency is the minimum frequency to cause photoelectric emission. Don't forget, we could also have this. That'd be a threshold wavelength. Okay? Well, we'll stick with this guy for a second. If I know what the threshold frequency is, I can find my work function. So let's do it for silver. I set across the axis about 1.2 times 10 to the 15th hertz. Multiply this by, by Planck's constant, and I get about 4.96 electron volts. Now, when I plotted it and carried my line down, I got about 4.7 electron volts. So I don't feel too bad about that. That's pretty decent. Do the same thing for platinum, 4.14 times 10 to the negative 15th, times that threshold frequency where it actually crossed the x-axis, and I got about 5.79 electron volts. Well, when I plotted this out and carried it down, I got about 5.6, and my resolution isn't real great on this graph, so I'm feeling pretty good that everything I've done has worked out pretty well. Now, what do we notice about the slopes? The slope of these lines are always equal to Planck's constant. Now, one thing you got to realize is this a wave or particle behavior of light? Light's going in like a little bundle, which means it's acting like a particle, okay? Little bundles are particle-like behavior. Does the particle model of light satisfy all behaviors of light? No, because we still have got diffraction and interference, and we've got no way of explaining that other than thinking about light as a wave. So we still need the wave model of light. Now, one thing I did want to talk to you about that AP asks about is dealing with intensity of a beam of light. The AP considers intensity of a beam of light as the power of the beam. Don't forget, power is energy per unit time. This can have unexpected effects on some of your answers. Let's say we've got two beams of light, a red beam and a violet beam. Both have the same intensity, which is your power, of 6 electron volts per second. A red photon has got energy of 2 electron volts. I'm picking numbers that just make this work very nicely. And a violet photon has got energy of 3 electron volts. How does this affect the number of photons per second? Well, in the red beam, if I've got 6 electron volts per second coming out of here, and each one of these guys is 2 electron volts, 2 electron volts, 2 electron volts, okay? That means I'm going to have 3 photons per second coming out of that beam. However, if I've got violet, I've got the same intensity, 6 electron volts per second. However, now I've got 2 3 electron volt photons coming out of there. So, for the same power, the red beam has more photons per second since there's less energy per photon. Okay? One other quick thing that I did want to talk to you about, and that's on the graph. Okay? I can do that graph a bunch of different ways. I can have frequency here, and on this side, I can have stopping potential in volts. And let's just say I've got 1, 2, 3, 4 volts. Keep in mind, since these are electrons, I can immediately say, if those are stopping potentials, since my kinetic energy is going to be equal to Q times V, and Q is going to be equal to 1 elementary charge, I can literally go like this. Because remember, the stopping potential is basically going to be 1-to-1 to whatever the energy is on those photons. All right? I know that was a lot to take in at once, but take a look at it. If you got to look over the video again, that's totally okay. I'm all right with that. I'm going to actually ask you guys to do some Regents questions on this. All right? I'm going to post a few Regents questions on here. Ask you guys to give a shot. Take a look at them. I want to take it easy on you. They should be in your packet. If not, it should be posted on the post that I put where I put the packet up earlier. Okay? And that's pretty much it, guys. I hope that everybody's doing okay. Families are doing okay. Everybody's taking care of each other, and stay away from people, please. This whole thing is just pretty much nightmarish. All right. I realize that for younger people, you might get a cold symptoms or something like that, but it's just scary all the way around. So do us a favor, do that social distancing, wash your hands, and I hope you guys are doing all right, and I'll talk to you guys tomorrow. All right, bye-bye.